Are we alone in the vastness of the cosmos? Today, I invite you to embark on an extraordinary journey, a journey that stretches beyond the stars, beyond the familiar constellations, to explore one of humanity's greatest questions. Is there life beyond our pale blue dot? If this question stirs your curiosity, I encourage you to like and share this video so that more seekers of the unknown can join this adventure. For centuries, the night sky has been a canvas of wonder and mystery. Every sparkling star, every shimmering galaxy, holds the promise of stories yet untold, worlds yet undiscovered. The universe, infinite and profound, beckons us to look up and wonder. Among the countless stars scattered like diamonds across the velvet blackness, could there be others like our sun, cradling planets where life might have taken root? Could there be beings looking back at us with the same wonder? Our quest to find alien life is as old as humanity itself. Ancient civilizations gazed at the heavens, crafting myths and legends about celestial beings and otherworldly realms. Yet in the modern age, science has transformed these stories into testable hypotheses. Astronomy, biology, chemistry, and technology converge to illuminate the shadowed corners of the universe, seeking evidence of life beyond Earth. This search is not merely an academic pursuit. It is a profound exploration of our own place in the cosmos. The sheer scale of the universe challenges the imagination. There are over 2 trillion galaxies, each containing billions of stars, many of which host planets. Recent advances in telescope technology have revealed thousands of exoplanets, worlds orbiting stars other than our sun, some nestled within what scientists call the habitable zone, where conditions might be right for life to flourish. These discoveries ignite hope and fuel questions. What is life? How does it arise? Could it be that the universe is teeming with life, or are we the lone sparks in an endless night? Life on Earth is a testament to the remarkable resilience and adaptability of nature. From the deepest ocean trenches to the driest deserts, life thrives in extreme conditions once thought inhospitable. This resilience broadens our perspective on where life might exist. Could similar forms, or entirely different, life forms survive in the harsh climates of distant planets or moons? Could life have emerged in the icy subsurface oceans of Europa, one of Jupiter's moons, or in the methane lakes of Saturn's moon Titan? The scientific search for extraterrestrial life takes many forms. One avenue is the search for microbial life within our own solar system. Mars, our red neighbor, holds particular intrigue. Evidence suggests that liquid water once flowed across its surface, and beneath its frozen crust, reservoirs of salty water may still exist. Missions such as NASA's Perseverance rover and the European Space Agency's upcoming ExoMars rover are designed to probe Mars's geology and search for biosignatures, clues that life once existed or still does. Beyond our solar system, the search becomes even more ambitious. The study of exoplanets through space telescopes like Kepler and TESS provides a map of potential habitats. Yet, detecting life at such great distances requires more than identifying planets. It demands the ability to detect signs of life through their atmospheres, through what we call biosignatures. These could be gases like oxygen or methane in unusual concentrations, indicating biological processes. Another frontier is the search for intelligent life. The SETI Institute, among others, listens for signals from distant civilizations, deliberate transmissions or unintended radio waves that could reveal the presence of advanced beings. Despite decades of searching, no definitive contact has yet been made. Yet the absence of evidence is not evidence of absence. The universe is vast, and the silence may be due to the limits of our current technology or the immense distances separating us. The philosophical implications of discovering extraterrestrial life are profound. Such a discovery would redefine our understanding of biology, evolution, and our place in the universe. It would challenge many beliefs and inspire new perspectives about life's diversity and interconnectedness. Whether we find microbial life in a Martian soil sample or receive a signal from a distant civilization, The impact on humanity's collective consciousness would be transformative. For now, our journey continues, driven by curiosity and the desire to understand the cosmos. We refine our instruments, send spacecraft to distant worlds, and listen intently to the silent whispers of space. Each step brings us closer to answering the timeless question, are we alone? The stars above hold secrets, and through the lens of science and imagination, we strive to uncover them. The universe is waiting, vast, silent, and full of possibilities. And as we look up into the night, we carry with us the hope that somewhere, out there, life stirs, reaching toward the unknown just as we do. The story of life on Earth is deeply intertwined with the story of the cosmos. Our planet, a fragile jewel orbiting a middle-aged star, is a cradle of complexity and diversity. But how did life begin here, and what can that tell us about its potential existence elsewhere? The origin of life, known scientifically as abiogenesis, remains one of the greatest mysteries in biology. It challenges us to understand how inanimate molecules could organize themselves into self-replicating entities, the first spark of life. Earth's early environment was harsh and volatile, bombarded by asteroids and ravaged by volcanic activity. Yet within this tumultuous setting, simple organic molecules gradually assembled. Hydrothermal vents deep in the oceans, rich in minerals and energy, are thought to have provided the perfect conditions for life's beginnings. These vents offer a compelling model for how life might arise elsewhere, not necessarily on warm, sunlit surfaces, but in hidden, extreme environments. If life emerged from such humble origins on Earth, it suggests that the ingredients and conditions necessary for life might be common throughout the universe. The basic building blocks of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are abundant in space. Complex organic molecules have been detected in interstellar clouds, comets, and meteorites, hinting that the chemistry of life is widespread. Yet, life as we know it depends on liquid water, a solvent capable of dissolving molecules and enabling chemical reactions. Water's unique properties have made it central to biology on Earth. This is why scientists focus so intently on locating water beyond our planet. Mars, Europa, Enceladus, and even distant exoplanets in habitable zones all offer tantalizing possibilities for liquid water, and by extension, life. But could life be fundamentally different elsewhere? Our Earth-centric view might limit our imagination. Some scientists propose that life could exist in forms vastly unlike terrestrial biology, based on silicon instead of carbon, or thriving in solvents other than water, such as liquid methane or ammonia. These ideas expand the horizon of astrobiology and remind us that the universe's creativity may far exceed our expectations. The search for life also brings with it profound technical challenges. Detecting biosignatures across interstellar distances requires extraordinary precision. Instruments must analyze faint light spectra from distant planets, parsing subtle signals from overwhelming cosmic noise. Planned missions like the James Webb Space Telescope and future observatories will deepen our ability to characterize exoplanet atmospheres and search for chemical signs of life. Closer to home, robotic explorers continue to advance our understanding of our solar neighbors. Mars rovers analyze soil and rock samples, searching for organic molecules or patterns that might signal past life. Missions to icy moons like Europa and Enceladus aim to penetrate their frozen crusts to study subsurface oceans, where life might be shielded from harsh radiation and conditions on the surface. The discovery of life, even microbial elsewhere, in our solar system would be revolutionary. It would suggest that life arises readily given the right conditions, and that Earth is not unique. Alternatively, if no life is found despite these efforts, it would raise profound questions about the rarity and fragility of life's emergence. Meanwhile, the search for extraterrestrial intelligence, SETI, challenges us to listen carefully and patiently The universe's vast distances mean that any signals we detect may have traveled for decades, centuries, or millennia. The messages, if they exist, could come from civilizations long gone or newly arisen. They might communicate in ways we cannot yet comprehend, or broadcast signals we have not yet learned to detect. The Fermi paradox encapsulates this enigma. Given the vast number of stars and potentially habitable planets, why have we not yet found clear evidence of extraterrestrial civilizations? Numerous hypotheses attempt to resolve this paradox, from the idea that advanced civilizations self-destruct to the notion that they deliberately avoid contact. Others speculate that life is common, but intelligence is rare, or that cosmic distances and the speed of light limit communication. Humanity's place in the cosmos is both humbling and inspiring. Our species, tiny on a cosmic scale, has developed the ability to peer into the depths of space, to question existence itself, and to seek companionship beyond our world. The endeavor to find life beyond Earth is a testament to human curiosity and our yearning to connect with something greater than ourselves. In this quest, we are explorers not only of the universe but of our own nature, our hopes, fears, and dreams. The search for alien life compels us to reflect on what it means to be alive, to be sentient, and to belong to a universe that may be far richer and stranger than we ever imagined. As technology progresses, as telescopes sharpen their gaze, and as missions venture farther into space, the possibility of discovery grows ever nearer. The night sky that once inspired myths and legends now challenges us to unravel scientific truths. And perhaps one day we will learn that we are not alone. The universe is not only vast in size, but ancient in time. It has been evolving for over 13 billion years, providing a staggering temporal expanse for life to potentially arise and flourish somewhere beyond Earth. Our planet is relatively young, a mere 4.5 billion years old, and life here has existed for nearly 3.5 billion years. This timeline suggests that life might have had ample opportunity to develop elsewhere, perhaps long before humans ever walked the Earth. When we look at the cosmic timeline, we realize that distant stars and planets may have formed billions of years before our sun ignited. Some of these stars are part of ancient galaxies, with planetary systems that have been stable for eons. Such longevity raises the possibility that if life began on these planets, it might have evolved far beyond simple microbes, potentially to civilizations capable of interstellar communication or travel. The study of extremophiles on Earth gives insight into the resilience and adaptability of life. These are organisms that survive in environments once considered utterly inhospitable: acidic hot springs, the crushing depths of the ocean, radioactive waste, and even the frozen deserts of Antarctica. The existence of such hardy life forms expands the criteria for habitability. If life can endure these extremes on Earth, why not on other worlds that seem hostile by human standards? The concept of the habitable zone has traditionally been defined as the region around a star where liquid water can exist on a planet's surface. But recent discoveries challenge this narrow view. For example, subsurface oceans beneath icy crusts of moons like Europa and Enceladus could provide stable, energy-rich environments sheltered from harsh space radiation. Such hidden habitats might be teeming with microbial life, hidden from our direct view. Advances in astrobiology also explore the chemistry that might underpin alien life. Life on Earth is carbon-based, with DNA and RNA as the molecules that store and transmit genetic information. However, scientists speculate that other molecules or even unknown biochemistries could exist elsewhere. Silicon, for example, shares some chemical properties with carbon and might form the backbone of exotic life forms. Alternatively, life could use different solvents such as liquid methane or ethane, which exist on Saturn's moon Titan. Searching for life beyond Earth involves not only seeking direct evidence, but also understanding how life influences its environment. On Earth, life has dramatically transformed the atmosphere over billions of years, producing oxygen and other gases that are detectable even from space. By studying exoplanet atmospheres for these biosignatures, scientists hope to identify planets where life is actively altering the environment. The discovery of exoplanets revolutionized our understanding of the universe's potential for life. Before the 1990s, planets beyond our solar system were purely speculative. Now, thousands have been confirmed, revealing astonishing diversity. Some are gas giants larger than Jupiter. Others are rocky worlds similar in size to Earth. Many orbit close to their stars, while others inhabit the temperate zones where conditions might support life. However, mere presence in the habitable zone is not enough. Planetary conditions such as atmosphere composition, magnetic fields, geological activity, and even the presence of a large moon can influence habitability. Earth's magnetic field protects us from harmful solar radiation, and our moon stabilizes the planet's axial tilt, contributing to a relatively stable climate. Such complex factors remind us that life's emergence depends on a delicate balance. Astrobiologists also examine how life could be detected remotely. The concept of technosignatures refers to evidence of technology or industrial activity, artificial light, radio signals, or pollution in planetary atmospheres. Detecting such signs would suggest not just life, but intelligent life capable of altering their environment in measurable ways. Yet the vast distances and enormous timescales involve present daunting challenges. The speed of light limits how quickly we can receive signals or send probes. Even the nearest stars are light years away, meaning any message we receive is ancient history. This reality tempers our expectations, but also fuels the desire to innovate, to develop new technologies capable of reaching deeper and farther into space. Our pursuit of alien life also intersects with profound ethical questions. How would contact with extraterrestrial life change our societies, beliefs, and worldviews? How should we respond to such a discovery? Would humanity unite in wonder and cooperation, or would fear and division prevail? These questions remind us that the search for life beyond Earth is also a search within ourselves. As we push the boundaries of exploration, the universe continually humbles us with its immensity and mystery. Each discovery, a new exoplanet, a chemical signature, a curious anomaly, adds a piece to the cosmic puzzle. The silence of space is profound, yet it speaks volumes about the challenges and hopes of finding companionship in the void. In this grand cosmic quest, we stand at the threshold of profound discovery. The answer to whether we are alone might lie just beyond our reach, waiting for our instruments to catch the faintest whisper, the tiniest clue that life exists elsewhere. Until then, we watch the stars, hopeful and determined, bound by our shared desire to understand the universe and our place within it. The story of searching for alien life is also a story of technology and ingenuity. Humanity's ability to reach beyond our terrestrial confines has been enabled by generations of scientists, engineers, and visionaries who dared to imagine a universe filled with possibilities. From the earliest radio telescopes to the sophisticated space probes now traversing the solar system, each advance has opened new windows on the cosmos. Radio astronomy, born in the 20th century, became a powerful tool in the search for extraterrestrial intelligence. Radio waves travel vast distances across the vacuum of space, unaffected by interstellar dust that blocks visible light. Early pioneers hypothesized that intelligent civilizations might broadcast signals intentionally or unintentionally. Projects like SETI, the search for extraterrestrial intelligence, began scanning the skies for patterns, narrow-band signals that do not occur naturally and might indicate artificial origin. The quest for intelligent signals is complex and requires patience. The cosmic haystack is vast, with billions of frequencies and an infinite expanse of sky. Scientists must discern faint whispers from the universe's natural noise, and they develop algorithms to detect repeating patterns or anomalies. Despite decades of listening, no confirmed signals have been detected, leading to new questions and hypotheses about the nature and behavior of potential civilizations. Beyond listening, humanity has also attempted to send messages into space. The Arecibo message, transmitted in 1974, was a binary-coded greeting aimed at a distant star cluster. It encoded basic information about humanity and our solar system, our DNA, and simple images. Such attempts raise debates about whether we should reveal our presence or remain silent, uncertain of what we might attract. Space probes such as Voyager 1 and 2 carry golden records, phonograph discs containing sounds and images representing life on Earth, intended as time capsules for any advanced beings that might encounter them. These artifacts symbolize humanity's hope and desire to reach out across the cosmic ocean, a testament to our longing for connection. Robotic exploration of our solar system has brought us closer to understanding where life might exist. Mars has been a prime target, with multiple missions investigating its geology and searching for signs of past or present life. The discovery of ancient riverbeds, minerals that form in water, and seasonal methane spikes hints that Mars once had conditions potentially favorable to life. Icy moons such as Europa and Enceladus have captured scientific imagination. Beneath their thick ice shells lie vast oceans, kept liquid by tidal heating. The detection of plumes ejecting water vapor and organic molecules from these moons suggests active geochemistry and potential habitats for life. Upcoming missions like Europa Clipper aim to probe these environments more closely, seeking the chemical fingerprints that life might leave behind. In parallel, the discovery of exoplanets has revolutionized astrobiology. Space telescopes like Kepler and TESS have identified thousands of planets orbiting other stars, including many Earth-sized worlds in their stars' habitable zones. Characterizing these distant worlds' atmospheres and surfaces has become a priority, with the hope of finding biosignatures, gases or patterns indicative of life processes. The next generation of telescopes will push the boundaries of observation further. The James Webb Space Telescope, launched with capabilities to analyze atmospheric composition, will peer into the infrared spectrum where signatures of water, oxygen, methane, and other molecules can be detected. Ground-based observatories equipped with powerful spectrographs will complement these efforts. Even as technology advances, scientists remain cautious. Many potential biosignatures can be mimicked by abiotic processes, requiring careful interpretation. The search for life is as much about eliminating false positives as it is about detecting true signals. It demands interdisciplinary collaboration, integrating astronomy, chemistry, geology, and biology. This search also inspires philosophical reflection. If life is discovered elsewhere, it challenges the anthropocentric view of the universe. It invites us to reconsider our uniqueness and the ethical responsibilities that come with knowledge of other living beings. How would humanity respond to evidence of microbial life on Mars or signs of intelligence beyond our solar system? Conversely, the absence of detected life despite our efforts might underscore the preciousness and rarity of life on Earth. It would emphasize the importance of stewardship of our planet and the urgent need to preserve its delicate ecosystems. Whether we find company among the stars or not, the search itself enriches our understanding of life and the cosmos. In the silence between stars, humanity listens and watches, ever hopeful. The quest for alien life is not only a scientific pursuit, but a deeply human endeavor, a quest for meaning, belonging, and connection in the vastness of space. It invites us to dream, to explore, and to imagine what lies beyond the familiar glow of our own world. Life, as we know it, relies on a delicate interplay of chemical elements and energy flows. Carbon, hydrogen, oxygen, and nitrogen form the building blocks of all known organisms, weaving together in complex molecules that carry genetic information and catalyze biological processes. This familiar biochemistry shapes the search for life elsewhere, guiding scientists to look for similar patterns beyond Earth. Yet the vast diversity of life on our own planet challenges any simplistic definition. From single-celled bacteria to towering redwoods, From creatures thriving near volcanic vents to those soaring in the skies, life adapts and thrives in unexpected ways. This biological versatility hints at the possibility that life elsewhere may take forms unimaginable to us, shaped by alien environments, unique chemistries, and different evolutionary pressures. Astrobiologists consider the essential requirements for life: a solvent to facilitate chemical reactions, a source of energy, and a stable environment for molecular complexity to emerge. Water, with its remarkable properties, is the prime candidate. Its polarity enables the formation of complex organic molecules, and its liquid state fosters dynamic biochemical interactions. But other solvents, such as liquid methane or ammonia, might serve similar roles in colder or chemically distinct worlds. Energy sources are equally vital. On Earth, sunlight drives photosynthesis, powering ecosystems. Yet many life forms rely on chemical energy derived from hydrothermal vents or chemical gradients in the absence of sunlight. This broadens the scope of possible habitats beyond Earth's surface, extending to subsurface oceans and rocky interiors. The concept of panspermia explores the idea that life might not have originated on Earth at all, but arrived from elsewhere, carried on comets or meteorites. Organic molecules, some complex and life-forming, have been detected on asteroids and in interstellar clouds, suggesting that the ingredients for life are widespread. If life can hitch a ride across space, the cosmos could be interconnected by biological threads stretching across time and distance. The origin of life itself remains one of science's greatest mysteries. How simple molecules gave rise to self-replicating systems capable of evolution is still debated. Experiments simulate early Earth conditions, demonstrating how amino acids and nucleotides can form spontaneously. Yet the leap to living cells involves numerous unknown steps. Understanding this transition could illuminate the probability of life emerging elsewhere. One of the central challenges in detecting extraterrestrial life is distinguishing between biological and abiotic signatures. For example, methane can be produced both by living organisms and geological processes. Oxygen in an atmosphere may indicate photosynthesis, but can also arise from photochemical reactions. Therefore, scientists look for multiple lines of evidence, including atmospheric composition, surface features, and temporal changes. The search for biosignatures extends beyond our solar system. Spectroscopy allows us to analyze light filtered through exoplanet atmospheres, seeking molecules that might signal life. Observing changes over time, such as seasonal variations in gas concentrations, could provide further clues. In the future, direct imaging of exoplanet surfaces may reveal vegetation-like pigments or other biological markers. Parallel to the search for biosignatures is the quest for technosignatures, indications of technology and intelligence. These might include radio or laser transmissions, megastructures orbiting stars, or pollution in planetary atmospheres. The discovery of technosignatures would be transformative, signaling not only life but minds, capable of altering their environment on grand scales. The famous Drake equation attempts to estimate the number of civilizations in our galaxy by considering factors such as star formation rates, fraction of stars with planets, and likelihood of life and intelligence developing. While many of its variables remain uncertain, the equation frames the scientific and philosophical debate about our cosmic loneliness or company. One paradox confronting this debate is the Fermi paradox, the contradiction between the high probability estimates of extraterrestrial civilizations and the lack of evidence or contact. Proposed solutions range from the rarity of life, self-destruction of civilizations, to the possibility that advanced life chooses not to communicate or remains hidden. As humanity advances technologically, our capacity to detect and understand signs of life improves. The interplay of observation, experimentation, and theoretical modeling brings us closer to answering the profound question of our uniqueness. Each discovery, from water ice on distant moons to complex organic molecules in space, adds to a growing mosaic of cosmic habitability. The search also reflects humanity's own yearning for meaning and connection. To find life beyond Earth would reshape our understanding of ourselves and our place in the cosmos. It would challenge religious, philosophical, and cultural perspectives, inviting new narratives about life's universality or exceptionalism. In the vast darkness dotted with countless stars, the question remains, are we alone or part of a grander community of life? The answer, hidden in the fabric of space and time, beckons us onward. With curiosity as our guide and technology as our tool, we continue to explore, listen, and wonder, reaching for the stars and perhaps for a cosmic companion. The cosmos stretches beyond comprehension, a vast expanse filled with mysteries yet to be unraveled. Among its most compelling enigmas is the origin of life, not just on Earth, but throughout the universe. While Earth remains the only known cradle of life, the immense variety of planetary environments discovered in recent decades has expanded our horizons and reshaped our understanding of where life might exist. The story begins with the formation of stars and planets. Within swirling clouds of gas and dust, gravity pulls matter together, igniting nuclear fusion at the core of new stars. Around these stars, disks of material coalesce into planets, moons, and smaller bodies. The diversity of these systems is astonishing, from hot Jupiters orbiting perilously close to their stars, to cold, rocky worlds drifting in the outer reaches. Among the key ingredients for life is liquid water, a solvent with unparalleled properties essential for biochemical reactions. Earth's fortunate position within the Sun's habitable zone, where temperatures allow water to remain liquid, is a critical factor in the emergence of life here. But habitability is not limited to this narrow zone alone. Icy moons such as Europa, orbiting Jupiter, and Enceladus, circling Saturn, harbor vast oceans beneath their frozen surfaces. These hidden seas, warmed by tidal forces generated through gravitational interactions with their parent planets, present intriguing possibilities for life. The discovery of hydrothermal activity beneath these icy shells suggests environments rich in energy and nutrients, analogous to Earth's deep ocean vents where life thrives despite the absence of sunlight. On Earth, extremophils, organisms that live in extreme environments such as acidic springs, deep-sea vents, or radioactive waste, reveal life's remarkable adaptability. These resilient life forms push the boundaries of what we consider habitable, implying that extraterrestrial life might exist in conditions once thought hostile. The search for life also leads to the study of organic molecules, the carbon-based compounds essential to all known living systems. Complex organics have been detected in comets, meteorites, and interstellar clouds, indicating that the raw materials for life are widespread in the cosmos. Laboratory simulations show that simple molecules can evolve into more complex precursors under appropriate conditions. Mars, our nearest planetary neighbor, continues to captivate scientists with tantalizing clues. Ancient riverbeds, minerals formed in watery environments, and transient methane plumes suggest Mars was once wetter and possibly hospitable to life. Though no definitive evidence has yet been found, robotic missions like Perseverance are exploring Martian soil for biosignatures and ancient microbial life. Beyond our solar system, the discovery of exoplanets revolutionizes the search. Thousands of planets orbiting distant stars have been catalogued, many residing in their star's habitable zone. Advances in telescope technology allow scientists to analyze the atmospheres of these worlds, seeking gases like oxygen, ozone, or methane, which could indicate biological activity. The possibility of life on these distant planets raises profound questions. What forms might it take? Would it be microbial or complex? Could intelligent life have emerged, and if so, what would it look like? The vast distances between stars make direct contact or travel currently impossible, yet the detection of life's fingerprints would be a monumental revelation. Astrobiology, an interdisciplinary science, merges astronomy, biology, chemistry, and geology to approach these questions. It studies life's origins, distribution, and future in the universe. It challenges our assumptions, reminding us that life's manifestations may be diverse and surprising. Ethical considerations arise as humanity extends its reach. If life is discovered, how should we interact? Should we protect extraterrestrial ecosystems from contamination or exploitation? The principle of planetary protection guides missions to avoid harmful interference, preserving potential habitats for future study. The quest also carries existential weight. Finding life elsewhere would reshape humanity's self-image, dissolving the notion of Earth as the sole sanctuary of life. It would invite reflection on our shared biological heritage and the fragile nature of existence. In this grand cosmic journey, every discovery, every unanswered question deepens our awe and curiosity. The universe, vast and ancient, holds stories written in starlight and shadow, awaiting those who dare to listen. The silence of the cosmos is profound, yet it speaks volumes to those who listen carefully. Humanity's gaze turns ever outward, searching for signs not only of life but of intelligence, civilizations that might share the cosmic stage. The challenge of detecting intelligent life is as much about understanding ourselves as it is about finding others. The idea that other civilizations might exist has inspired countless theories and explorations. The famous Drake equation offers a framework to estimate the number of communicative civilizations in the Milky Way. Though many parameters remain uncertain, it highlights the variables that influence the emergence and detectability of intelligent life: star formation rates, planetary system frequency, habitability, and longevity of technological societies. Our search has included scanning the skies for artificial signals. Radio telescopes sweep the heavens, listening for patterns that stand out against the natural background. Narrow bandwidth transmissions or pulsed signals that cannot be explained by natural astrophysical processes. These signals, if found, could indicate deliberate communication or leakage from technological activities. Despite the vast effort, no definitive signal has yet been identified. This absence, known as the Great Silence, raises profound questions. Is intelligent life rare or transient? Are civilizations too distant in space or time to communicate? Or do advanced societies choose to remain silent, perhaps out of caution or indifference? The Fermi paradox encapsulates this dilemma. If intelligent life is common, why have we not yet seen any evidence? Proposed solutions range from the possibility that civilizations self-destruct to the idea that advanced beings use communication methods beyond our detection, such as quantum entanglement or neutrino signaling. Another consideration is the time factor. The universe is 13.8 billion years old, and technological civilizations might have risen and fallen long before humanity emerged. Our brief technological era may be but a fleeting moment in cosmic time, making overlap with other civilizations unlikely. Efforts to send messages into space have included the Arecibo message, and more recent, METI, messaging extraterrestrial, intelligence initiatives. These transmissions encode information about human culture, biology, and mathematics, aiming to reach potential listeners. The ethics of actively broadcasting our presence remain debated, balancing the desire for connection against possible risks. Technosignatures extend beyond radio waves. Scientists search for infrared excesses that might indicate waste heat from large-scale energy usage, or unusual light patterns suggestive of megastructures built around stars. Such anomalies could reveal civilizations harnessing energy on a grand scale, as proposed in the hypothetical Dyson spheres. Exploring our own solar system also informs this search. While no evidence of alien technology has been found, the possibility of past or present microbial life raises questions about life's trajectory and the evolution of intelligence. Understanding how life evolves complexity and cognition here may illuminate the likelihood of intelligence elsewhere. Philosophically, the search for alien intelligence challenges our notions of consciousness and identity. What defines intelligence? Would alien minds share our emotions, values, or social structures? The diversity of life on Earth suggests that cognition can take many forms, and extraterrestrial intelligence might be radically different. The discovery of extraterrestrial intelligence would be transformative. It would herald a new era of cosmic understanding, forcing humanity to reconsider its place in the universe. The social, religious, and cultural impacts would be profound, inspiring awe, fear, and hope. In the meantime, the search continues, a testament to human curiosity and resilience. As we scan the starry night, we listen not only for signals but for meaning, seeking connection across the silence, and pondering the question that has haunted us for centuries. Are we alone? The vastness of the universe humbles the imagination. Yet within this immensity, the search for life is grounded in precise, patient observation and daring speculation. As technology advances, so too does our capacity to peer deeper into the cosmos and unravel its secrets. One of the most promising fields in this quest is the study of exoplanets, worlds orbiting stars beyond our sun. Since the first confirmed discovery in the 1990s, thousands of exoplanets have been identified, ranging from gas giants larger than Jupiter to rocky Earth-sized bodies. Some lie within their star's habitable zone, where conditions might allow liquid water to exist. The diversity among these planets is staggering. Some are tidally locked, with one side perpetually facing their star while the other remains in darkness. Others orbit multiple stars or follow eccentric paths. Their atmospheres vary widely, from thick clouds of sulfuric acid to thin, icy shells. Each new discovery reshapes the map of where life might emerge. To study these distant worlds, scientists use sophisticated methods. Transit photometry observes the slight dimming of a star as a planet passes in front, revealing size and orbit. Spectroscopy analyzes the starlight filtered through a planet's atmosphere, detecting gases and molecules. These techniques hint at the presence of water vapor, oxygen, methane, and other compounds linked to life. Future telescopes, both space-based and ground observatories, promise greater sensitivity and resolution. Projects like the James Webb Space Telescope and the upcoming Extremely Large Telescope aim to characterize exoplanet atmospheres in unprecedented detail. With luck, signs of biological activity might soon be discerned. Meanwhile, our own solar system offers intriguing laboratories for astrobiology. Mars missions probe its dry, dusty surface and ancient river valleys for traces of microbial life or organic compounds. The icy moons Europa and Enceladus, with subsurface oceans beneath their frozen crusts, beckon with their promise of hidden habitats. The discovery of plumes erupting from Enceladus's south pole, spewing water vapor and organic molecules into space, has intensified interest. Sampling these plumes might reveal evidence of life without landing on the moon itself. Similarly, Europa's cracked, shifting ice conceals an ocean that could be warmed by tidal heating, possibly supporting ecosystems. Titan, Saturn's largest moon, presents another fascinating case. Its thick nitrogen-rich atmosphere and methane lakes create a chemically rich environment. While radically different from Earth, Titan's complex organic chemistry could provide clues to alternative forms of life. These missions exemplify humanity's growing commitment to exploring the habitability of other worlds. Robotic explorers, orbiters, and landers extend our senses beyond Earth, collecting data that challenge and refine our understanding. As we contemplate the possibility of life elsewhere, we are reminded of the delicate balance that sustains life here. Earth's biosphere is a dynamic system where geology, atmosphere, oceans, and living organisms intertwine in a fragile harmony. This perspective fuels a renewed sense of stewardship for our own planet. The search for alien life is not only about discovery, but also about perspective. It reveals our place within a vast, interconnected cosmos, urging humility and curiosity. Whether life is common or rare, the quest inspires science, philosophy, and wonder. In the unfolding story of the universe, we stand at a threshold, poised, to move from speculation to knowledge, from isolation to potential companionship. The answers lie in the stars, waiting for us to listen and understand. As the search for life beyond Earth intensifies, one question emerges with increasing clarity. What defines life itself? This seemingly simple inquiry holds profound implications. For our quest, Earth's life forms are all carbon-based, relying on water as a solvent and following a complex chain of biological processes. But might life elsewhere operate on fundamentally different principles? The answer lies at the intersection of biology, chemistry, and physics. Life, in its broadest sense, is a system capable of self-replication, metabolism, and evolution. Earth, DNA encodes genetic information. Proteins catalyze reactions, and cells create the structures of living beings. Yet this familiar model is but one example of life's potential manifestations. Astrobiologists consider alternative biochemistries that might flourish in environments unlike Earth's. Silicon-based life, though hypothetical, is often proposed due to silicon's chemical similarities to carbon. Other possibilities include ammonia as a solvent instead of water, or exotic energy sources such as chemical gradients or radiation. Exploring these ideas expands the criteria for habitability. Planets once dismissed as barren might host life forms adapted to extremes, superheated atmospheres, frozen wastelands, or acidic seas. This diversity challenges the anthropocentric view that life must mirror Earth's conditions. Laboratory. Experiments simulate these environments, testing how molecules assemble and react under varying pressures, temperatures, and chemistries. Findings suggest that the building blocks of life can form under a range of circumstances, hinting at life's potential ubiquity. Yet detecting such life remotely poses formidable challenges. Traditional biosignatures like oxygen or methane might not apply universally. Instead, scientists search for anomalies, patterns, or compounds difficult to explain through abiotic processes alone. The field of synthetic biology offers additional insights. By engineering novel life forms and biological systems, researchers explore life's flexibility and constraints. This work informs the design of instruments and missions seeking extraterrestrial life, broadening the scope of detectable phenomena. This conceptual expansion invites humility. Life beyond Earth, if found, may be so alien in form and function that recognizing it requires new frameworks and open minds. Our definitions, grounded in earthly experience, must evolve to encompass the unknown. The implications extend beyond science to philosophy and culture. Discovering non-Earth-like life would challenge our understanding of biology, consciousness, and our place in the cosmos. It could inspire a new era of exploration and reflection, reshaping humanity's narrative. Meanwhile, the search continues with unwavering dedication. From robotic explorers on Mars to telescopes peering across the galaxy, humanity probes the cosmos for signs of life's universal dance. Each discovery, each new question, brings us closer to unraveling the profound mystery of existence. In contemplating life's possibilities, we embrace a universe rich with potential, a canvas painted with the colors of chance and necessity, inviting us to explore and wonder. Amid the vastness of space and the multitude of worlds, the search for extraterrestrial life confronts profound mysteries about the origin of life itself. On Earth, life arose from simple molecules in a process known as abiogenesis, a transformation from chemistry to biology that remains only partially understood. Unraveling this transition is key to comprehending whether life is a cosmic inevitability or a rare miracle. Early Earth was a turbulent place, bombarded by asteroids, volcanic eruptions, and lightning storms. Within this chaos, complex organic molecules formed, setting the stage for the first living systems. The primordial soup, rich with amino acids and nucleotides, slowly organized into self-replicating molecules, a crucial step toward life. Laboratory. Experiments have recreated aspects of this primordial chemistry, demonstrating how simple compounds can assemble into more complex structures under plausible early Earth conditions. These findings suggest that life's building blocks may be common throughout the cosmos, emerging wherever suitable environments exist. Another pathway to life may involve hydrothermal vents deep beneath the ocean, where mineral-rich water provides energy and catalytic surfaces. Such environments might have fostered the first metabolic networks, independent of sunlight. The discovery of extremophiles thriving in these harsh conditions expands the realm of possible habitats. Panspermia offers a complementary perspective, proposing that life or its precursors might have been delivered to Earth via comets or meteorites. Organic molecules found in these space rocks, including amino acids and sugars, support this idea. If panspermia is widespread, life could be seeded across the galaxy, linking distant worlds in a shared biological heritage. Understanding life's origins informs our search strategies. It guides the selection of target environments, the design of detection instruments, and the interpretation of ambiguous data. The transition from chemistry to biology remains one of the most profound puzzles in science. If life is indeed common in the universe, it likely arises from a combination of chance, chemistry, and environmental conditions. This perspective instills a sense of cosmic connection, a thread weaving through the fabric of existence, linking stars, planets, and living beings. Yet the emergence of life is just the beginning. Its persistence, evolution, and complexity depend on countless factors. Earth's history reveals a delicate interplay between life and environment, punctuated by mass extinctions and bursts of diversification. The search for life beyond Earth challenges us to reconsider our assumptions and expand our understanding. It pushes the boundaries of science and imagination, bridging the gap between what we know and what we dare to dream. In the unfolding, cosmic story, every discovery is a step closer to answering the age-old question: are we alone or part of a greater tapestry of life stretching across the stars? The universe speaks in many languages, and among them, light is the most profound. It carries messages from distant stars and planets, encoded in spectra and photons, revealing secrets of composition, motion, and history. In our search for alien life, deciphering these luminous signals is a crucial endeavor. Spectroscopy allows us to analyze the atmospheres of distant exoplanets, detecting the fingerprints of molecules that could hint at biological processes. Oxygen and methane, when found together, suggest chemical disequilibrium, potentially caused by life. Water vapor signals habitability, while other gases hint at geological or even biological activity. Yet interpreting these signals is complex. Planetary atmospheres are dynamic and influenced by a myriad of factors: volcanism, radiation, impacts. Distinguishing biological signatures from abiotic processes demands careful modeling and observation. False positives and negatives challenge our understanding and urge caution. Beyond atmospheric studies, scientists examine the surface and environmental conditions of nearby bodies in our solar system. Mars rovers analyze soil and rock samples, searching for organics and signs of past habitability. The icy moons of Jupiter and Saturn beckon with their subsurface oceans, potentially harboring life beneath thick ice. The search extends to unconventional markers, techno-signatures, that could reveal advanced civilizations. These include artificial radio signals, laser emissions, or even pollution in exoplanet atmospheres. The possibility of detecting such signs opens new avenues, blending astronomy with the study of technology and civilization. Our instruments grow ever more sensitive, capturing faint whispers across vast distances. The square-kilometer array, soon to be operational, will enhance our ability to detect faint radio emissions, scanning billions of stars for anomalies. This monumental effort exemplifies humanity's commitment to cosmic discovery. Simultaneously, citizen science projects engage the public in analyzing vast datasets, harnessing collective intelligence to spot unusual signals. This democratization of the search broadens participation and accelerates progress. The quest is not merely technical, it is profoundly human. It reflects our yearning to connect, to understand whether other minds ponder their place in the cosmos. Each observation, each null result, refines our knowledge and fuels hope. Ultimately, the universe's vastness is matched only by the depth of our curiosity. Through light and radio waves, dust and molecules, we seek companions in the cosmic night, reaching across space and time in search of kindred life. Within the vast theater of the cosmos, the question of intelligence emerges as a poignant dimension in the search for life. Simple microbial existence, though wondrous, carries a different weight than the possibility of civilizations reaching out across the stars. The idea of intelligent extraterrestrial life ignites imaginations and scientific inquiry alike. Intelligence, as we understand it, involves consciousness, self-awareness, problem-solving, and communication. On Earth, it has led to remarkable achievements: language, technology, art, and science. If such intelligence exists elsewhere, could it be communicating, building, or even watching us? The search for extraterrestrial intelligence, SETI, embodies this hope. For decades, it has scanned the skies for artificial signals, broadcasting silent invitations to unknown civilizations. Radio waves, chosen for their speed and reach, are scrutinized for patterns unlikely to arise naturally. While no confirmed signals have yet emerged, the search continues with renewed vigor. Advances in computing power and machine learning allow sifting through immense volumes of data, hunting for faint or complex signals. The absence of evidence is not evidence of absence, reminding us that silence could stem from distance, technology, or timing. The Fermi paradox confronts us with a puzzle. Given the vast number of stars and potentially habitable planets, why have we not detected signs of intelligent life? Various hypotheses attempt to resolve this enigma, from the rarity of intelligence to self-destruction, or perhaps the deliberate avoidance of contact. Another possibility is that advanced civilizations communicate in ways unfamiliar to us, through means beyond our current detection methods: quantum communication, neutrino beams, or other exotic technologies. This broadens the scope of SETI, inspiring innovative approaches and interdisciplinary collaboration. The idea of interstellar messages takes shape in projects like the Voyager Golden Record, launched into space with sounds and images of Earth. These artifacts embody a cosmic greeting, hopeful and humble, cast into the cosmic sea. Contemplating extraterrestrial intelligence challenges our understanding of life, culture, and the future. It asks us to consider what it means to be intelligent, to communicate, and to coexist. The discovery of even microbial life elsewhere would be profound, but contact with an intelligent species would reshape humanity's self-conception. This quest unites scientific rigor with profound philosophical questions. It drives us to listen more carefully, to look more deeply, and to imagine the infinite possibilities woven into the fabric of the universe. The search for alien intelligence is a mirror reflecting our own aspirations, fears, and hopes, a testament to the enduring human spirit seeking connection beyond the stars. Beyond the search for intelligent signals and microbial life, the exploration of our own solar system reveals tantalizing clues of potential habitats hidden in plain sight. Mars, our neighboring planet, has long been a focal point of curiosity and study. Once a warmer, wetter world, Mars shows geological evidence of ancient rivers, lakes, and possibly oceans. Could life have thrived in these vanished waters? Robotic. Explorers have uncovered compelling hints: organic molecules embedded in Martian soil, seasonal methane fluctuations in the atmosphere, and minerals formed in the presence of water. While not definitive proof, these findings ignite hope that microbial life might have emerged or may even persist beneath the surface. Further afield lie the icy moons of Jupiter and Saturn, Europa, Enceladus, and Titan. These worlds conceal subsurface oceans beneath thick crusts of ice, warmed by tidal forces from their giant planets. Enceladus famously erupts geysers of water vapor and organic compounds into space, providing accessible samples of its hidden ocean. Titan, with its dense atmosphere and lakes of liquid methane and ethane, presents a unique laboratory for studying alternative chemistries of life. Its complex organic haze and hydrocarbon cycles challenge Earth-centric notions of habitability. Missions such as Europa Clipper and Dragonfly aim to probe these moons more closely, searching for biosignatures and signs of active biology. These endeavors highlight the importance of in situ exploration, venturing directly to the environments where life might dwell. The technological challenges are immense, penetrating thick ice layers, detecting faint chemical signals, and operating in extreme conditions require innovation and perseverance. Yet the potential rewards are extraordinary. Finding life closer to home would transform our understanding of biology and the distribution of life in the cosmos. The exploration of our solar system thus serves as both a proving ground and a beacon of possibility. It bridges the gap between distant speculation and tangible discovery, bringing the cosmic search within reach. This frontier reminds us that the universe's secrets are not only far away, but sometimes hidden just beneath our feet or beneath alien ice. It inspires a spirit of adventure, curiosity, and humility, acknowledging how much remains to be learned. As we reach outward and inward, we carry with us the hope that life, in its myriad forms, may be woven throughout the cosmos, a profound revelation that would forever change our place in the grand tapestry of existence. The quest for alien. Life also unfolds in the study of extreme environments on Earth, places once thought inhospitable, yet teeming with resilient organisms. These extremophiles reveal the incredible adaptability of life, reshaping our understanding of its boundaries and suggesting new possibilities for life beyond Earth. From scalding hydrothermal vents deep beneath the oceans to acidic hot springs, frozen tundras and radioactive wastelands, life persists in forms and processes that challenge traditional biology. Microbes survive by harnessing chemical energy from minerals, adapting their cellular machinery to withstand extremes of temperature, pressure, and radiation. These terrestrial analogs serve as models for extraterrestrial habitats. The icy moons, with subsurface oceans, might harbor similar ecosystems around hydrothermal vents, where chemical gradients provide energy. Mars's subsurface, shielded from harsh surface radiation, could sustain microbial communities if water and nutrients exist. The resilience of extremophiles broadens the search for biosignatures. It suggests that life might thrive in niches previously dismissed, adapting to conditions vastly different from Earth's temperate surface. This insight informs the design of instruments and missions, guiding where and how we seek life. Furthermore, extremophile research deepens our understanding of life's origins and evolution. It illustrates that life's emergence is not limited to gentle, Earth-like environments, but can arise and persist amid volatility and adversity. This paints a picture of life as a tenacious force, potentially widespread throughout the cosmos. The study of extremophiles also inspires astrobiological experiments in space, testing how terrestrial life survives in microgravity, radiation, and vacuum. These experiments inform planetary protection policies, preventing contamination of other worlds and preserving the integrity of our search. By examining life at Earth's extremes, we glimpse the possibilities that await beyond our planet. We recognize that life's tenacity may extend far beyond familiar frontiers, expanding the horizons of habitability and hope. In this endeavor, science, exploration, and imagination converge, driving humanity's profound quest to understand whether life exists elsewhere and what forms it might take. As we contemplate the possibility of life beyond Earth, the idea of communication, both receiving and sending messages, opens a profound dialogue about our place in the cosmos. The attempt to reach out to potential alien civilizations is an expression of hope, curiosity, and the fundamental human desire to connect. Deliberate efforts such as the Arecibo message sent in 1974 encoded information about humanity, our DNA, and our solar system into a radio signal aimed at a distant star cluster. This symbolic act encapsulates our yearning to introduce ourselves to the cosmic community. More recent initiatives like METI, Messaging Extraterrestrial Intelligence, raise complex questions. What should we say? Who speaks for humanity? Is it wise to broadcast our presence, potentially revealing our location to unknown civilizations? These questions reflect deep philosophical and ethical considerations. The possibility of contact challenges our assumptions about safety, diplomacy, and the consequences of making our existence known. The search for signals from space, passive listening, has been the primary approach, motivated by caution. Yet, the silence we've detected so far compels some to advocate for more active engagement, believing that the benefits of contact could be transformative. Simultaneously, scientists explore non-radio means of communication, including optical signals, like laser pulses, which could carry tightly focused messages across vast distances. These methods may overcome the limitations of radio and open new channels for interstellar dialogue. The idea of cosmic messages extends to the realms of symbolism and mathematics. Many searchers hope that any intelligent civilization would recognize universal patterns, prime numbers, Fibonacci sequences, or the chemical structure of life as signs of deliberate communication. This shared language of science and mathematics offers a bridge across unknown cultures and biologies, a beacon in the cosmic night. At the heart of this pursuit lies the question of understanding, whether we can comprehend alien minds, or whether their thoughts, senses, and perceptions differ so fundamentally that communication becomes a near impossible challenge. Yet, this uncertainty does not deter the search. Instead, it fuels it, driving humanity's imagination and technological progress. In reaching outward, we are also reaching inward, confronting what it means to be human, to be a communicator, and to seek companionship in the vast, silent universe. The silence of the cosmos, often described as a deafening quiet, invites reflection on the nature of life, time, and evolution. If the universe teems with life, why does this silence persist? Could it be that civilizations arise and vanish in fleeting moments caught in the delicate balance between creation and extinction? The cosmic timeline spans billions of years, yet intelligent life may have only recently emerged, or could have arisen eons ago, long extinct before we appeared. Our brief tenure in this vast epoch might limit overlap with other civilizations. Some theories suggest that civilizations self-destruct through technological misuse, environmental collapse, or internal conflict, never reaching a stage of interstellar communication. This somber perspective, sometimes called the Great Filter, warns of existential risks that humanity must confront to survive and thrive. Alternatively, advanced civilizations may choose silence deliberately, abiding by a cosmic code of non-interference, observing but not disturbing emerging species. This zoo hypothesis imagines Earth as a sanctuary, protected and watched from afar. The vast distances between stars impose further challenges. Even at light speed, messages take years or centuries to arrive. This latency hampers dialogue, making real-time exchange impossible and reducing communication to brief, isolated encounters. Moreover, our methods of searching, primarily electromagnetic signals, may miss other forms of communication beyond our current understanding or detection capabilities. Life may use modalities we cannot yet conceive. In this context, the search for life becomes a meditation on patience, humility, and perseverance. It teaches us to appreciate our own fragile existence and the preciousness of life in all its forms. This contemplation also inspires stewardship of our planet and the nurturing of intelligence and culture here on Earth. For in safeguarding our future, we honor the cosmic lineage of life and the possibility of connection. The silence invites, not despair but wonder, a call to keep listening, learning, and dreaming amid the vast night. The profound implications of discovering alien life extend beyond science and technology. They touch the core of human identity, philosophy, and spirituality. What would it mean for humanity to know we are not alone? Such a revelation could reshape our understanding of ourselves, dissolving the ancient notion of human exceptionalism and inviting us to see ourselves as part of a greater cosmic community. It might spark new questions about consciousness, purpose, and the nature of life itself. Religious and philosophical traditions would face new dialogues, integrating the cosmic perspective with long-held beliefs. The discovery of life elsewhere could enrich spiritual understanding or challenge existing paradigms, prompting a profound reevaluation of meaning. Ethical questions would arise. How should we treat alien life, particularly if it is microbial or primitive? What responsibilities would we bear in interacting with or protecting these life forms? Would we extend concepts of rights and respect beyond Earth? The societal impact could be profound, uniting humanity with a shared sense of curiosity and humility, or conversely stirring fear and uncertainty. Our response would reveal much about our collective values, resilience, and capacity for adaptation. Moreover, the discovery of extraterrestrial intelligence might revolutionize science and technology. New knowledge from alien civilizations, if accessible, could propel humanity toward breakthroughs in medicine, energy, and exploration. The potential cultural exchange, even if indirect, promises to expand horizons and inspire generations, fueling dreams of exploration and understanding. At the heart of this profound quest lies the enduring human spirit, a spirit driven by wonder, courage, and hope. Whether we find life in distant stars or in the hidden oceans of our solar system, the journey itself enriches us, deepening our connection to the cosmos and to each other. This quest reminds us that we are explorers, not just of space but of meaning, purpose, and belonging in the infinite expanse of existence. The future of the search for alien life rests on the shoulders of technological innovation and global collaboration. New telescopes, both on Earth and in space, promise to revolutionize our ability to detect and study exoplanets and their atmospheres. Instruments like the James Webb Space Telescope open windows to worlds previously beyond our reach, analyzing atmospheric compositions for potential signs of life. Spectroscopy allows us to identify gases such as oxygen, methane, and carbon dioxide in exoplanet atmospheres, molecules that in certain combinations may indicate biological activity. The subtle fingerprint of these biosignatures fuels optimism about discovering habitable or inhabited worlds. Simultaneously, advances in artificial intelligence and data analysis empower scientists to sift through the astronomical data deluge, detecting patterns and anomalies invisible to the human eye. Machine learning algorithms enhance the search for faint signals and unusual phenomena, accelerating discovery. International partnerships unite agencies, universities, and researchers across borders, pooling resources and expertise. This collaborative spirit reflects the universal nature of the quest, a pursuit that transcends national boundaries and cultural differences. Beyond professional astronomy, citizen science projects invite the public to participate in the search, fostering a shared sense of wonder and engagement. From classifying galaxies to identifying potential signals, these efforts democratize discovery and inspire new generations. At the same time, ethical considerations guide exploration. Planetary protection protocols aim to prevent biological contamination of other worlds and safeguard Earth from potential extraterrestrial agents, balancing exploration with responsibility. As technology propels us forward, the dream of detecting life beyond Earth shifts from imagination to tangible possibility. Each discovery, each mission, brings us closer to answering the age-old question, are we alone? The path ahead is uncertain, filled with challenges and wonder. Yet it is a journey defined by human curiosity, resilience, and hope. The search for life beyond our world is not only a scientific endeavor, but a profound narrative about who we are and what we seek in the vast cosmic ocean. The profound silence that has greeted our search so far challenges us to consider not only where life might exist, but how it might manifest. Life on Earth is carbon-based, reliant on liquid water and a narrow range of environmental conditions. Yet the universe may harbor life forms that defy our terrestrial expectations. Speculative biology explores these possibilities, imagining life built on silicon, thriving in ammonia oceans, or existing in exotic environments like gas giants' atmospheres. These thought experiments expand our conception of habitability and encourage open-mindedness. Such diversity, if realized, would challenge humanity's understanding of biology and evolution, revealing the creativity and adaptability of life's processes. We may find life forms that communicate through light, use chemical languages unfamiliar to us, or possess senses beyond human perception. This diversity also underscores the importance of humility in our search. Our instruments and methods are designed based on Earth's life. We might overlook or misinterpret signs of alien life simply because it is fundamentally different. As we refine our tools and broaden our perspectives, we edge closer to recognizing life in its many possible forms. This effort requires interdisciplinary collaboration, integrating astronomy, biology, chemistry, and even philosophy. The search for alien life thus becomes a journey not only into the cosmos, but into the nature of life itself. It challenges us to rethink definitions, embrace complexity, and appreciate the mystery that underlies existence. Whether life elsewhere is a mirror of ourselves or a stranger beyond imagining, its discovery would forever alter our place in the universe, reminding us that life is a phenomenon, both fragile and magnificent. The search for alien life is ultimately a testament to humanity's enduring spirit of exploration and hope. It reflects our deep yearning to understand the cosmos and our place within it. Whether or not we find definitive evidence, the journey itself enriches our knowledge, inspires innovation, and connects us to the vast universe. In contemplating the possibility of life beyond Earth, we are invited to reflect on the preciousness of our own world, a fragile oasis in the cosmic wilderness. This awareness calls us to stewardship, to protect and cherish the diversity of life that flourishes here. The quest also reminds us that we are part of a larger story, woven into the fabric of space and time. Each star we observe, each planet we study, expands the horizon of our curiosity and dreams. As technology advances and our gaze extends ever farther, the hope remains alive that one day, perhaps soon, we will answer the question that has fascinated humanity for millennia. Are we alone? Until that moment arrives, the search continues, driven by wonder, perseverance, and the timeless human desire to connect with others beyond ourselves. In this cosmic silence, we listen with open hearts and minds, ready to embrace whatever discovery awaits. This is the story of our quest, a story without end, unfolding across the infinite night.